Hey kids, Math here. Got chapter 5 D&S constructed response FRQs. This is solutions this week or this assignment. This one had a couple pretty neat parts to these three questions on this unit. The first one is basically starting us out with urea, which is a real interesting compound. We're going to draw its structure here in a sec for you to see what I say when I say that's interesting. Urea is a nice organic-y base because of that NH2s on the outside. They've given us molar masses, so we're going to do some calculations there. And we're comparing that to something called methoxyethane. And that's an ether that we're not really going to get to talking about too much in here, but we're going to find out there's a polarity difference between the two. So let's look at number 1A first. Calculate the molarity of 25 mils that contains 27 grams. This should be really a slam dunk. 27 grams. They gave us in the problem 60 grams per mole. And boom, that gives us 0.45 moles. Hey, you're putting that in 0.025 liters. And we've got an 18 molar solution going on there. So 1A, boom, done did it. B says, account for the differences in solubility of urea and methoxyethane in terms of forces between the solute and the solvent molecules. Well, this is really hard to do. So I'm going to skip B and I'm going to come back to it after I've done C. It's not that B is hard. B will just be a lot easier once we see the Lewis structures for these that we draw. So let's look at this. It tells us that we have an NH2 bonded to a carbon with an oxygen on it, bonded to another NH2. Now you see why this is a really interesting molecule, because we have bases on each end of the molecule, pardon the phrase, but we call these dibasic. It has two bases on it, those ammonias. And of course, yes, my oxygens have their lone pairs, back off, okay? And now we're gonna compare that to methoxyethane, which is just going to be, as shown, CH3 bonded to a CH2 bonded to an O bonded to a CH3. I can't do that. So now when we look at these, and yes, my oxygen still has lone pairs, no worries there. But now when we go back to B and it says account for differences in solubility, the methoxy here, this is very symmetrical. This is a non-polar molecule. And so we'd say the methoxy is non-polar and insoluble in water, whereas the urea is polar. Polar is all get out. Nitrogen's everywhere, oxygen's everywhere. I mean, this, hang on a minute. So it's going to be soluble in H2O. Understand what I'm saying is the methoxy molecule is much more symmetrical and much more saturated. When I look at the urea molecule, I have nitrogens that are terminal. Those are going to tend to be a little polar. And I've got oxygen sticking up here as a tail. Holy moly, that's a polar end of that molecule. So that's going to increase its solubility in water. More polar, more soluble in water. You guys know that. So we've drawn those. Use the structure in C to sketch two different kinds of interactions of water with the urea molecule. And so I'm going to redraw my urea down here just to give me a little bit of room. And I'll go NH2 to C to O to NH2. And now you'll see, well, I understand I'm going to get 1 real easily. And so my H from my water, OH, lone pair, and then put another water up here and go H, OH, lone pair. And now let's find our IMFs, bink, 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 and bink, 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 bink. That you've got the nitrogen to the hydrogen, nitrogen to hydrogen, and the hydrogen to the oxygen. So you have 2 different intermolecular forces that are going on there. So a lot of bonding going on with these intermolecular forces as well in this video. That's kind of cool. Okay, so that's 1. Now 2, it says titrate. And I don't want anybody freaking out on me going, wait a minute, there's no titrations on here. This is really pretty simple stuff. So the first one says, list the pieces of equipment that we're going to need. Well, for A to perform this, you're going to need a pipette, and that's going to be to measure the H2SO4. You're going to need a burette, and that's going to be to add exact amounts of the NaOH. Sorry for that. All right, they're just trying to feel you out. Do you understand, or can you use the correct terms for pieces of glassware? And that seems pretty reasonable. Okay, in B it says list the measurements that must be made to determine the molarity. Now this is classic because we're titrating with NaOH and we're determining the molarity of H2SO4. So what measurements need to be made? Don't give us a lab procedure. You guys have heard that lecture before. What do we need? We need to know the volume of the H2SO4, and we need to know the volume of the NaOH. And someone's going to say, but you also need to know the molarity of the NaOH, and that's kind of true. But did you measure that? No, you didn't. These are the only 2 measurements, and they don't ask for any explanation. List measurements, done. C, describe briefly how the student can tell when the reaction is complete. I'm going to use an indicator, and I'm going to look for a color change at the equivalence point. Okay, no problem. Now, for 4 successive titrations were made here, and we've got these 3 pieces of data. I've got 2355, 2346, 2348. Guess what? 2266, we're going to call an outlier. We're going to average those and come up with an average of 23.50. And I think that's enough of a rationale for our measurement. Okay, I know you guys know how to do the calculation part of it. 2 down. Three is a really neat question. And I kind of like this because it's reactions. So A says, identify each as an acid base, redox, and or a precipitate reaction. So let's look at A. A, we've got Na3PO4, blah, 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 blah. It's 2 ionic compounds, looks like double replacement, should lead me to a precipitation reaction. So the first one's going to be a precipitation reaction because Ca3 PO42. That's my precipitate. That's going to be a solid. In B, definitely acid base. but also a precipitate. And it's got a darling molecule in there, BaSO4. Sulfates are soluble except for barium. Watch that one, kids. Watch it close. That barium sulfate will come back and get you. And then, of course, the third one has to be my redox. And we've got a lot of reasons there that are going to explain that. You'll see when I finally write the equations for y'all. As B says, balance each. So I'm going to go 2 Na3PO4s plus 3 CaNO3 goes to 1 Ca3PO42 plus 6 NaNO3s. Okay. Second one comes off pretty good. You've got H2SO4 and you've got BaOH2. In the acid, the sulfuric, I've got 2 protons, 2 H's. In the base, I've got 2 hydroxides. So I'm going to make 2 waters. And I'm going to make that precipitate BaSO4. And then in 3, I've got K2Cr2O7. Anytime you see that chromate dichromate, expect there to be redox. 3 SnCl2s goes to, whoops. Back it up, Steve. Plus 14 HCl's goes to 2 CrCl3s plus 3 SnCl4s plus 7 H2Os plus 2 KCl's. Woo! There's a lot going on in that equation. That one took a little while. Then it says in C, give the formula of the base. So C number 1, the base is going to be BaOH2. That's easy. In 2, it says, for the redox reaction, identify the oxidizer and state the number of electrons gained. Well, I've already said, be careful, be leery. Whenever you see dichromate, you all should know by now that's +6. And look at your chromium over here. Excuse me. That was +3. So within a unit, my oxidizer, K2Cr2O7, all right, and the number of electrons is 6 electrons, because for every chromium, it's going down 3. It's absorbing 3 electrons. There are 2 chromiums, so it's going to do that twice. And then, of course, for 3, we've got what's the precipitate? We've already said multiple times, BaSO4 comes on here. So a real neat question under the guise of solutions is it's talking about acid base, it's talking about precipitation, it's talking about redox, as well as some of the titration that's solutions. Remember, chapter 4 was aqueous environments, and we can't overlook that. So we do need to pay attention to some of this stuff, even if it uses the word titration. Let's not veer away from that. Let's pick up those points. I'm Smath. I hope this video helped you.